Let's take a look at some properties of these summations. So the first one here, we have the sum from I equals 1 to n of k times a sub I. So k here is, you can see that the index, which is the variable for the summation, is I, and so k is not. So k is some sort of constant. And this constant is being multiplied times each one of the terms of the sequence all the way up to n. Well, we saw from a previous example that this constant is going to be common to every single one of the terms of the sequence, so it can be factored out. So instead of factoring it out later, why don't you factor it out at the very beginning? So any constant can be factored out right there into the outside of the summation. So constants can be taken out. Okay, all right then. The next one is this. So this is one of my most favorite things to say, honestly. All right, so notice that what we have here is we have a sum of a sum or a difference. And what this property is saying is that the sum of a sum or difference is the sum or difference of the sums. What? Did that make sense to you? Here, look at this again. The sum of a sum or a difference. So here, this is the sum of a sum or difference is the sum or difference of the two sums, right? Oh, that makes perfect sense. So what this basically says is that if you've got two sets of things that you're adding up, you can either add up the terms term by term, or you can add up all the first set of terms plus all the second set of terms and then just add or subtract the two individual sums, right? Okay. All right, let's look at some formulae for each a set of sums, and these I want to say were in your summer assignment that some of you probably totally did not do. Okay, so here's the sum of constants. Let's say, for example, I have the sum from I equals 1 to n and c. C is definitely not the variable here, so it doesn't change. So its sum is equal to c times n. Here, let me just show you, demonstrate this just for a second of why this one should make sense. Come down here, add an extra little page so I don't spoil. Oh, I've already spoiled everything. No, that's not where I want that page. This is where I want this page. So this summation from I equals 1, let's say that we just do I equals 1 to 5 of the number, I don't know, 4. So now the number 4 does not change. I go to stick in the number 1 into 4, and all I get is a 4. Whoops, is a 4. Plus, okay, so then my index is supposed to increase by 1, so it's going to go to 2. So I got to stick 2 in here. I don't get anything, so I got to keep it as a 4. Plus, and I do it with 3, and I get another 4. I do it with 4, and I get another 4, and I do it with 5, and I get another 4. So, of course, notice that there are 5 copies of that number 4, so it's essentially 5 times 4 to get 20. So notice that what we have here is we have the constant, whatever this constant number that's inside the sigma notation, that we're multiplying times the upper bound of that summation. So this number times this number, and that's exactly what the sum of that sequence was. Okay. All right, the sum of integers is the one that we did in the warm-up activity. It was the one that Gauss basically came up with. So the summation from I equals 1 to n of I, so it's 1 plus 2 plus 3 plus 4, and so on, all the way up to n is n times n plus 1 divided by 2. Again, that's the one that we came up with in the warm-up activity. And like I said, over the summer assignment, that's where these other ones came from, the sum of squares. So here what I'm doing is I'm adding up 1 squared plus 2 squared plus 3 squared plus 4 squared, and here's what the summation looks like. Summation from I equals 1 to n of I squared is equal to, you might have thought that all you have to do is square these things, square this sum, but no, that is not right. It is n times n plus 1 times 2n plus 1 over 6. Where does this sum come from? Well, in the summer assignment, the way that we did it was basically with the same kind of thing that you did with finite differences in algebra 2, right? So you can use a series of polynomials to come up with that. Likewise, you can do the same thing for the sum of cubes And so you want to take a guess what the sum of cubes is? So a sum of cubes again means 1 cubed plus 2 cubed plus 3 cubed and so on. And here it is. It is n squared times n plus 1 squared over 4. Wait a minute. Isn't that just the square of the integers? That's really, really bizarre. Okay, well, I've got one more of these for you. Now, before I show it to you, understand you do not have to have these memorized at all. If you have to use them, and you will in your little homework assignments, and to form kind of the foundation of these Riemann sums, which will eventually form the foundation of the definite integral, you just have to be able to use them. So if at any case, at any time that you need to use them, you'll have them written down someplace, either in your notes, on a sheet of paper, someplace. You don't have to have them memorized. And so here then is the sum of hypercubes to the fourth power, basically. So 1 to the fourth, 2 to the fourth, 3 to the fourth, and so on is, yeah, you can see it written there. All right, so I'm not going to read it out. All right. So go ahead and take yourself a moment to write each one of these things down in case they come up, because they're gonna. And they might come up starting right here with this final exercise of objective 1. We want to evaluate the sum from I equals 1 to n of 1 plus, how about I plus 1 over n squared for n equals 10, 100, 1,000, and 10,000. Okay, so one of the things that we could do is we could separately do, all right, so I'm just going to do this sum for 10 right here, right? And get that sum. And then we would do a separate sum for 100. And again, this n and this n are exactly the same. Or we could basically come up with some sort of formula involving n, and then when we're all done, we could just plug in 10, 100, and 1,000 and 10,000, right? And it's that second one that we are going to do. All right, so, oh man,